I am Jeroen van Meij and welcome to my lecture series on computer and network security. In this video series, I will talk about key distribution, or how to securely distribute encryption keys among communicating parties. In this first video, I will talk about distributing private keys using symmetric encryption methods. And recall that in symmetric encryption, the two communicating parties need to share a private key that no one else should have access to. The question therefore is, how do they exchange this key without others seeing it? And this can be done on one hand using other symmetric encryption methods or using asymmetric encryption. In this video we'll talk about using symmetric encryption and in the next one about using asymmetric encryption. And there are different methods to exchange this key. The first one is that the first party, A, the one that sends the data, selects a key and physically delivers that key to B. So they walk over to B and give them, for example, on a piece of paper, the private key. The second one is that they give this task to a third party. The third party will then select the key and deliver it physically to both A and B. This obviously needs to be a trusted third party because they will have access to this secret key. The third method is assuming A and B already share a private key. They can then encrypt the new key using the old one and transmit it over a network. The fourth method is similar to the third one, except that they don't share a private key with each other, but with a third party, C. C can then deliver the shared secret key between A and B over an encrypted link to both A and B separately. Again, here C needs to be a trusted third party. I have a question for you. Which of these four key distribution techniques are most desirable for end-to-end encryption between arbitrary parties A and B? Here, arbitrary refers to the fact that A and B are not known in advance and could be anyone involved in a large-scale network with many potential communicating parties. Feel free to pause the video if you want some time to think about it. And let's take a look at the correct answer. The correct answer is option D, namely a third party securely transmits the new key to A and B over an encrypted channel. And let's take a look at why the last option is the best one. Option 1 and 2, where a key is physically delivered, is obviously infeasible in a large-scale network with end-to-end encryption. The communicating parties may be very far away from each other, or there can be a lot of possible partners to communicate with. These two are referred to as out-of-band delivery, and therefore they are only useful in small-scale scenarios, such as, for example, when communicating between the sites of a company, where it is possible to physically deliver a key. The third approach, where we assume A and B already share a key and use that key to encrypt their new key and transmit it over a network, also has some issues. First of all, if an attacker can determine a single key, then all future keys will be compromised. Second, the approach can only be used in a small-scale scenario due to the amount of keys that need to be maintained. And let's take a closer look at how such a decentralized key exchange method would work. As I mentioned, it's only useful for small-scale scenarios, for example in a local network, as a lot of keys need to be maintained. And here you see how the key can be exchanged. We are assuming there's already a previously shared master key KM. The exchange is initiated by one of the two parties, for example A, and A sends its identifier and a randomly generated nonce N1 to the other communicating party B. B uses the previously shared secret key to encrypt a newly generated session key, or KS, the identifier of A, its own identifier, some transformation of the nonce n and a new nonce n2. A will then be able to decrypt this message, as they are already sharing a key km, and will send back some function of the nonce n2 sent by B, encrypted with ks. B will decrypt it and know the communication came from A, as the nonce was included. The reason for including this nonce is to avoid replay attacks and ensure that A and B are indeed the communicating parties, so that there is no man in the middle. And as I said, one of the downsides of this decentralized key control is the fact that a lot of keys are needed, because all parties that can potentially communicate already need to have a pre-shared key. So my question is, how many keys are needed for fully decentralized key control in a network consisting of n end hosts that all potentially want to communicate with one another? Is it n times n minus 1 divided by 2, n squared divided by 2, n divided by 2, n minus 1 divided by 2, or only 1? Feel free to pause the video and take some time to think about it. And let's take a look at the correct answer. The correct answer is n times n minus 1 divided by 2, because each of the n end hosts need to have a pre-shared key with the other n minus 1 hosts. Obviously, we divide this by 2, as the two-way communication could use the same key. And this obviously doesn't scale so well. With 1000 endpoints, 500,000 keys would be needed already. With 10,000, 50 million keys. And that's why, for symmetric key distribution using symmetric encryption, the use of a trusted third party, also known as a key distribution center, is the most widely used approach. And in the next video, I will talk about key distribution centers.